Well, here, let me just call it L1. Clean this up later if needed. Plus L2 plus L3 plus L4. L2, L3. All right, then we add in pairs of loops that don't touch each other. So if we look at this, we see loop 1 does not touch loop 2. So I've got L1, 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 L2. And I've got loop 1 does not touch loop 3. So I've got L1 and L3. And then I've got L1 and L4 do not touch each other. So I got another pair. So this is L1 and L, what happened? Wrong button. L4. And I think we're done with the pairs of loops. All right, I think we've covered them all. L1, L2. Are there any other pairs of loops that do not touch? I'll take back my previous statement. There's one more pair.
Is it L2, L4?
Yes.
Okay.
Very good. L2, L4. L2 and L4. Yeah. All right, now I think we're done. So here's L2 and L4 way over here. You know, they don't have anything in common, so that's good. So I think we've covered all the pairs. The next part are the triples. Those are subtracted off. Do we have any triples that do not touch? 3 loops that do not touch each other. We got one. We got L1. We got L2. And we got L4. I think that's it. Loop 1, loop 2, loop 4. The only triple that doesn't touch each other. All right, and then next part, back up, is delta 1. So we need a delta. Where's my delta? There. Delta 1 is equal to delta with all the loops that touch the path removed. So the path, remember, is G1, G2, G3, G4. Turns out every single loop has something in common with that path. So there's nothing else added to delta 1. So the transfer function just give me an equation. There we go. Transfer function. And what do we got? We got y. My input was called r. is equal to the path, which is here. Times delta 1. I think it's multiplied by delta 1, which is 1, divided by delta, which is all this stuff. So I got a 1 plus L1 plus L2 plus L3 plus L4. And these all have double negatives on them. So they're all positive terms. Should put my plus sign down here. A bunch of pluses. Loop 2 plus loop 3. Plus loop 4. All right, so those are all my first terms, and then I've got all these pairs of terms. So those go starting here, loop 1, loop 2, loop 1, loop 2, and then I've got loop 1, loop 3, so I need one of these. And loop 3. And that takes care of this term. So then I need loop 1, loop 4. Loop 1. Loop 4. And finally, loop 2, loop 4. It's getting big. Oops. And we got one more. We got the loop 1, loop 2, loop 4. We out here on the end. All right, loop 1. Copy. Loop 1, loop 2. And loop 4. There we go. Oh, how come that's so big? Anyway, that's the easy way to do it. Anything else is just going to be block diagram reduction is going to take much longer. Let's see if my my document camera is not cooperating. I don't know why. Try different USB ports. Do not know what's going on here. It starts and it stops. Okay, so it's not going to work. All right, moving right along. I don't know if I want to type all this stuff up. So let me see. We've got a transfer function. The feed forward or the open loop transfer function is given here. So what is the steady state error when the input is a unit step function? So how do you go about this? The easiest way is to use the final value theorem.
right? Final value term. So the final value theorem says you can use the Laplace function, Laplace domain function. You multiply it by s, and then you let s go to 0. Take the limit as s goes to 0. And that'll give you the final value in the time domain. Kind of handy, because this is a cubic, and you don't want to have to try to, close the loop, multiply by 1 over s to get the response, and then find the inverse Laplace transforms. Too much trouble. So the first step here is to get the closed loop transfer function. That's really what we need to do. Insert equation. Oh, let me see. We need the transfer function, so I'll call this y over r. This will be a lot of typing, but we know, what do we know about this? We know this is going to be equal to g over 1 plus g, right? Since there's no h in the feedback loop. All right, so g has a denominator, that cubic term. This is the denominator. So when I'm all said and done, I'm going to multiply top and bottom by this denominator to make it a rational expression. And when I do that, in the numerator, I'm going to have 9. And in the denominator, I'm going to wind up with this plus 9. If you want to, take a few minutes and check that out. A shortcut way of looking at closing the loop here is to put the numerator of the feed-forward transfer function in the numerator, and the denominator includes the numerator of the feed-forward and the denominator. So this is going to be what? This will be 12 down here. You might want to check that out. So this is the closed loop transfer function. So the response, y of s, y of s, is equal to 1 over s times this. Put a dot in here. Okay, so now, I don't think I need all these spaces in here. So now, the final value, let me see, how should I represent this? This would be, I'll call it y steady state is equal to, this is the final value, that's little y is time domain, steady state value is equal to the limit as s goes to 0 of s times, that s is part of the final value term, times this. Okay, so this is pretty good. I see this term is going to cancel this term, so I'm going to be left with this, and then I'm going to let s go to 0, so this cubic term drops out, squared term drops out, s term drops out. I'm left with 9 over 12. Looks like this would be equal to 9/12, which probably reduces to what, 3/4. So it looks like the final value is 3/4. So what would be the steady state error? Got one more operation here. The steady state error would be equal to the input, what would that be? R of t minus, and this is overkill, but I'll do it anyway. As t goes to infinity of the input minus the output. Okay, input is equal to 1, output is equal to 3/4. Steady state error is 1/4. Okay, any questions?
Nope.
Another way you could do that, here I found the final value of the response and then took the difference. You could also find the error in the Laplace domain. Yeah, I'll do this. So the error steady state in the Laplace domain would be equal to what? Limit as s goes to 0, s times a whole bunch of stuff. S times the input. Input is 1 over s minus the response, which is this. Okay, so in the Laplace domain, here's your input. Here's the response to a unit step input. The difference is the error. And if you multiply by s and let s go to 0, you get the steady state. You get the final value of the error. So this is E sub ss, time domain steady state error, as well as Laplace.
So for the response, the s's in the denominator canceled out because s was approaching 0, right?
Back here,
Yep, that step.
this s here is multiplied because that's part of the final value theorem. You can take any function in s, multiply it by s, let s go to 0, and that gives you the final value of that function.
Okay.
In the time domain. So this is part of the final value theorem. Down here, this s, that one, is part of the final value theorem. This is the input in Laplace, and this is the response in the Laplace domain. So you look at this, you say, okay, s cancels here, s cancels here. So what do you wind up with? You wind up with 1 minus 9/12, which is what we got here, which is 1/4. Okay, equals 1/4. Okay, any other questions? What else do we have? Oh, graphs. We got a lot of stuff here. Look at this. This says it's a bunch of closed loop first order system responses with a unit step input. let's see, let me see, what kind of questions would we ask about this? Let me back up a little bit. Let's bring this over here. This was last year's midterm. I think this problem came from there. All right, so you could ask a bunch of things about this. For instance, what's the time constant for these curves? What would be the time constant for curve number 1? This red thing. How would you estimate that? Well, I think you'd use this. It's a step input. So you do this. You look at the final value of the function up here. You take 63.2% of that, find this value, and then read the time at which that occurs, and that would be one time constant. So let's see if we can apply that. So it looks like the final value of this red curve is 0.5. So half of 0.632 is 0.32. So we come down here, we see here's 0.2, here's 0.3, here's 0.32, maybe right about here. Whoa, it looks like the time constant is 1/2. So that would be a good number for that for that question. Which of these curves exhibits the largest proportional gain? What do you think?
1.3.
Number 3?
No, one. I mean number 5.
Number 5?
Yes.
Yeah, that's probably an acceptable answer. I'd probably accept either number 3 or number 5. Number 5 is a bit special. If it's a proportional controller that we're talking about, then the only answer would be number 3. Right. If it's a PI controller, then the only answer would be number 5. So unless the type of controller is specified, either number 5 or number 3 would be acceptable. Okay, which one's the input? Easy question. Number 4, right? Okay, here's a more difficult question. If number 3 is the response proportional controller, what is the controller gain? What is K sub P for curve number 3? Assuming it's a proportional controller. Okay, so here we have to do some calculations. The equation for the response for closed loop first order system with a proportional controller is what? Well, it's the amplitude of the input times, let's go and multiply, times Kp over 1 plus KP. You guys remember this? If you don't, it's in your notes somewhere. Probably lab 2 notes. And then we multiply that by a bunch of stuff. We have the 1 minus e to the minus, do I need a division? Division. This would be what? This would be KP plus 1 times T divided by tau. There's tau. There's tau. Okay, so this is what your time domain response looks like. That's what this equation looks like. So all you have to do is recognize that time is pretty big. This term is negligible out here. So this is the amplitude of the response at steady state. So A is 1 because that's your input. All right, so what's KP? Well, let's see, the response is 0.8. 0.8 is equal to this. So what's KP equal to? Let me see, we got 0.8 plus 0.8 times KP, not K2, KP. So if I can do the algebra in my head, which is pretty risky. KP looks like it's going to be 0.8 plus 0.8 KP is equal to KP. Subtract 0.8. 0.8 is equal to 0.2 KP. 8 over 2, which is 4. KP is going to be equal to 4. Okay, does everybody follow that?
Yep.
All right, so let me see, what else can we say about this? What are the roots of equation 3? Or the characteristic equation for curve number 3? Are they real or are they complex conjugates? Let's see. How do we get at that anyway? Well, you look at the roots of the characteristic equation of the closed loop transfer function. It's a first order system, so there's only one root. So it's really kind of a dumb question. If you've only got one root, it's a first order equation, it's going to be real. You won't get complex conjugates unless it's a second order system. That's the only way you could possibly get complex conjugate roots for a system. So what else could we say? Take a look at curve 2 and curve 3. What do they have in common? 3 choices. Do they have the same time constant? Do they have the same proportional gain? Or do they have the same steady state error?
They appear to have similar time constants.
Yeah. To check that out, you'd have to, find 63% of 0.8 and 63% of 0.5. Come down here and find that they have the same time constant. Yeah. Okay. What else can we say? What's the steady state error of curve 2? Well, actually, I wouldn't want to ask that because the steady state error is the same as the final value. So it's 0.5, right? 0.5. Steady state error up here is 0.2. This is your error, steady state error up here. Which response is most likely from a PI controller?
Number 5.
Number 5. The integrator eliminates the steady state error. So up here you can tell there's no error, no steady state error. It oscillates, it overshoots, so it's probably got complex conjugate roots, second order equations, so yeah. That's about it. Let's go on. What else we got here? Let's see. Find the time domain response of the system below when subjected to a unit impulse. Huh. Okay. So what do we do here? Well, we got to get the closed loop transfer function. I think I inserted an equation up here. Didn't want to do that. Run it down here. Okay. So the closed loop transfer function is what? It's going to be y over r equal to, it's going to be a 3. Whoops. It's going to be a 3 divided by this. Okay, might want to check that out. See if that's right. Okay, so if it's a unit impulse, then we know that R is equal to 1. And this is R in the Laplace domain. This is the Laplace transform of a unit impulse. So all I have to do is multiply this by 1, and then find the inverse Laplace transform. And see what we get. So, out, so my equations look a little better. Come down here, insert y of s. Is equal to this, because r is equal to 1. So we got to go to table of Laplace transform pairs. And I got that here. So bring this over here. We look at the denominator, we see it's second order. It's got a constant in the numerator. Looks like this. That denominator matches with this. How can I show that? Okay, so I've got my s squared. 5 corresponds to 2 zeta omega n. And 4 corresponds to omega sub n squared. So I can put this in this form, or I can put this in this form if my numerator is the same as omega sub n squared. I can do that. I can do that. This is equal to this is equal to 1 sorry, let me back up. 4. This is equal to 3/4 times this. Okay, does everybody buy that? So I pull out a multiplying factor of 3/4, and now this equation exactly matches this form down here. So I know that omega sub n is squared is 4, so omega sub n must be 2. All right. So I've got 2 zeta times 2. I got 4 zeta is equal to 5. So zeta must be 4/5. I don't need that, but well, I guess I do need that. Let me write this out. Insert equation, couple equations. Omega sub n, where's omega? End of the alphabet. It's equal to 2. And zeta, Greek, go to Greek. Zeta is equal to, what do I have down here? I have 2 zeta omega n is equal to 5. So I got to divide by 5. It's 4/5. 4/5. It's equal to 0.8. Okay. So now my solution is here. This is my solution. So y of t is equal to omega sub n, which is 2, divided by square root 1 minus 0.8 squared times e to the minus zeta omega n. Zeta is 0.8, or let me see, it's 4/5 multiplied by 2, that's 8/5. 1.6, put it as 1.6 times t times the sine function, sine of 2t. Looks like that. So you can clean this up. This is 8 squared is what, 0.64? 1 minus 0.64 is 0.36, which sounds like 6 squared over 100, or yeah, I don't know. Anyway, you can clean this up some more. Put this as a decimal, and you're good to go. Any questions?
No.
All right, piece of cake, huh? What else do we have? I think this might be the last one that I've got here in this sample. This is impulse, obviously, right? Impulse response. So what are we supposed to do with this? Let's see. Let me back up. I think it's coming through here. This is older exam. There we go. Yeah, this is an impulse response. What's the time constant of this system? Assuming it's first order response. What's the time constant? A couple ways you can do this. You can look at this. You can find the initial value. Take, what would it be? 36.8% of that. That's where one time constant occurs. Or you can recognize when time is 0, amplitude is 1 over tau for unit impulse. So if it's specified that this is a unit impulse over here, then this value here, 5, is equal to 1 over the time constant. Y 0 equal to 1 over tau. What is tau? Oops. Equals 5. Tau, where'd tau go? Tau equals 0.2. That's pretty simple. Pretty simple. So those are all the examples that I've got. You'll need to be able to do take Laplace transforms. You'll need to be able to find inverse Laplace transforms. Sometimes there was no example that I presented here, but sometimes you'll have to do partial fraction expansion before you do inverse Laplace transforms. So you might want to review that. You'll need to know final value theorem. You'll need to be able to determine what the final value of a Laplace function is. You'll need to be able to determine steady state error. You'll need to know what responses look like from, say, this example. You need to be able to categorize these different types of responses. Know what kind of system would generate these different responses. Be able to find some parameters from these, such as the gain for this third curve that we found, time constant for this, identify which ones would come from a proportional controller versus a PI controller, which one is open loop, which one would be closed loop. If I had a curve that came up like this, you can imagine my cursor. I don't think I have any way to draw on this. If it came up like this and reached the final value of the input, you should know that that would be an open loop response. Remember the first lab, the open loop response took a long time, but it went up to the final value of the input for a step response. For a ramp response, open loop, looks like this, right? Looks like that. For a closed loop, these two are not parallel. The response is not parallel to the input. They diverge. So you should be able to identify the type of controller for a given system based on its characteristic response. All right, so I think that's about it. You guys have any questions, comments?
I'm guessing we need our graphs for the test or the charts with the equations for Laplace and stuff.
Yeah, take, where is it? Yeah, have this with you as a reference. And you can have this with you too, you know. Anything I handed out is fine. You need a calculator, obviously. Any notes that you've got are fine. No phone a friend, of course.
Are we taking this in class or through Blackboard?
This is in class.
Okay, just making sure.
Blackboard is just awful when it comes to exams. And quizzes,
Yep.
as you guys have found out most recently in this class. So it's just awful. I hate it. So yeah, it's in class. Monday, a midterm, and then a Wednesday group, different midterm. Same topics, different problems. And they'll all be, you know, similar to what we've done here. So, anything else? So don't everybody show up on Wednesday because we only got room for 10 seats. COVID capacity says 9, but I think we've got 10 tables available. So make sure you come on your designated day so we don't overpopulate one of the days.
Are you gonna post this session on the Blackboard?
Yeah, this has been recorded, and I will.
Thank you.
I think we're done here. So.
The recording has stopped.
I think that's about it. So have a good rest of afternoon, and we'll see you later on.
All right. Thanks, Dr. Etherton.
All
Enjoy.
right.
Thanks to you as well.